Here, when studying differential equations, it is very important to identify some certain special types of solutions, and the simplest of them is an equilibrium solution, right? So which is simply a constant. But of course, the derivative of a constant is 0, and it means that in order to find equilibrium solutions, we just take the right-hand side of our differential equation and equate it to 0. So geometrically, in the direction field, it means that there will be like a whole line where all the arrows are exactly horizontal, right? So all the arrows along this line, the arrows of the direction field, are exactly horizontal, because here the right hand side of the differential equation is 0, right? So here 0, but since it is 0, it means that all these vectors along this line are just 1, 0. Alright, here is another example how we can find equilibrium solutions. So here is the third example, right? So here it is a little bit more complicated. So notice that the right hand side depends not only on y but also on t. So here both t and y are involved. Right? So if y were constant, then the right hand side would be 0, because the derivative of a constant is 0. But then we would get a contradiction, because solving the right hand side equating to 0, we do not get a constant. Right, so sometimes there is no equilibrium solution. Alright, equilibrium solutions are important because they are related to asymptotic behavior. Right, so as I said in the beginning, with differential equations, very often we cannot solve them explicitly, but instead we can somehow figure out how solutions of differential equations behave as for different values of t. And probably the simplest of such behaviors is asymptotic behavior as t approaches infinity. And here from the picture we just see that, you know, if you try to plot a few solutions of this differential equation, right? So let me use another color. So they seem to be approaching the same line that is somewhere here, and this line of course is the equilibrium solution, because here along this line all the arrows will be exactly horizontal, right? And we conclude that from the direction field we see that all solutions, they approach, as t goes to infinity, they approach 4.9, because 4.9 is the horizontal line, is the equilibrium solution of this differential equation. Alright, so here is another example, right? So what is the behavior of solutions as t approach infinity? So the first step is to find equilibrium solutions, right? And there are two, 1 and 2. And now we plot the direction field. So notice that the important part is that here the right hand side is positive if y is bigger than 2, is negative if y is between 1 and 2, and positive again when y is smaller than 1. Now positive means that the arrow, all the arrows here, they point a little bit upward. Sometimes of course they're steeper, sometimes they're more horizontal, but anyway it is upward, so which means that here solutions increase. So here solutions will decrease because arrows point downward. The sign of the right hand side is negative, so y prime is negative, so y is decreasing. And here, because of the same logic, y is increasing. And putting this picture together with our calculations for equilibrium solutions, we see that and we will see that all solutions here, they kind of slowly, gradually approach the line y equals 1, so here they will also approach line y equals 1, but here they will very quickly go towards infinity. Right? And therefore we conclude that depending on y of 0, if y of 0 is less than 2, then the limit is 1. If it is exactly 2, then it just remains 2. But if y of 0 is bigger than 2, then the limit is infinity. So that's what we saw from the direction field.